Namaskar. Today we'll be talking about how LLMs, large language models, work internally. We'll get into the details of transformers architecture and how we will see how LLMs use this model to generate text. Large language models, LLMs, are a class of artificial intelligence models designed to process and generate human-like language. They are deep learning models that leverage massive amounts of text data to learn patterns, semantics, and context within language. These models have become increasingly sophisticated over time and have demonstrated remarkable capabilities in understanding, generating, and manipulating text. In this session, we shall be looking at the architecture which inspired large language models like GPT. GPT stands for Generative Pre-trained Transformer. This is a sample response by GPT when asked to write a review of a movie. And to understand how GPT works, attention is all you need. Yes, I'm talking about the revolutionary paper published in 2017 by Google researchers which proposed Transformers architecture, and it revolutionized the way neural networks process sequential data, addressing some of the limitations of RNNs and LSTMs. This is the representation diagram borrowed from the paper itself, which describes the internals of the Transformers architecture. In the context of generative AI, Transformers became catalyst for the development of LLMs. Large language models based upon the Transformer architecture, the generative capabilities in the top. LLMs like GPT, Generative Pre-trained Transformer, have clearly demonstrated a proficiency in generating coherent contextually relevant text across a multitude of topics. We shall be discussing how Transformers architecture work internally. On the first look, the architecture looks quite complex. So let us simplify this. A transformer architecture can be divided in two main components: encoder and decoder. These two components work in conjunction with each other and are quite similar in terms of internal components. Input is provided in tokenized form. Machines cannot understand raw text. Hence, before passing text into the model, we must first tokenize the words, or in simpler terms, convert words into numbers. We can choose from multiple tokenized methods, but we must make sure same algorithm for tokenizer is used when generating text in decoder component. Next step is to pass the tokenized input to a trainable vector embedding space, which is a high dimensional space where each token is represented as a vector and occupies a unique location within that space. Each token ID is matched to a multi-dimensional vector. And the intention is to make these vectors learn to encode the meaning and context of individual tokens in the input sequence. Here in the sample representation, we have a sample text represented in three-dimensional space. We can see how we can relate words that are located close to each other in the embedding space: history and reading. Sentences: I love reading history. We can also calculate the distance between words as an angle, which gives the model the ability to mathematically understand language. Original Transformers architecture used 512 dimensional space to represent the input. Here, for the sake of brevity, we have just represented simple sentence into three-dimensional space. Once the token vectors are added into the base of encoder or decoder, we must add positional encoding. Reason being, the model processes each of the input tokens in parallel. Hence, by adding the positional encoding, model preserves the information about the word order and does not lose the relevance of the position of the word in the sentence. Once we have summed the input tokens and positional encodings, we pass the resulting vectors to the self-attention layer, which is present in both components, encoder and decoder. Here the model analyzes the relationship between tokens in your input sequence. The self-attention mechanism allows the model to attend to different parts of the input sequence to better capture contextual dependencies between the words. The self-attention weights that are learned during the training and stored in these layers reflect the importance of each word in that input sequence to all other words in the sequence. However, transformer architecture make use of multiple sets of self-attention mechanism in parallel, referred to as heads, This multi-head attention mechanism enables the model to capture different types of relationships and dependencies between words. This means that multiple sets of self-attention weights or heads are learned in parallel, independently of each other. The number of attention heads included in the attention layer varies from model to model, but numbers in the range of 12 to 100 are common. Intuition here is that each attention head will learn a different aspect of the language. For example, one head may see the relationship between people or entities in our sentence, whilst the another head may focus on the activity of the sentence. Yet another head may focus on some other properties such as words, rhymes. It is important to note that you don't dictate ahead of time what aspects of the language the attention heads will learn. The weights of each head are randomly initialized and given sufficient training data and time, and each will learn different aspects of language. The outputs of these heads are concatenated and linearly transformed to produce the final self-attention output. Now that the transformer architecture has looked closely at different parts of the input data and figure out the importance and applied attention weights, model would like to make use of this understanding to predict what comes next. Hence, the output is processed through a fully connected feed-forward network. The encoder's feed-forward network consists of nonlinear activation functions, typically followed by linear transformations. This introduces complex transformation to representations, allowing the model to capture intricate relationships and patterns in the data. One of the motivations behind feed-forward network is to reduce the dimensionality of the representation while retaining maximum information. The output of this layer is a vector of logits proportional to the probability score of each token in the tokenizer dictionary. These logits are passed to a final softmax output layer where they are normalized into a probability score for each word. These numbers represent how likely each word in the vocabulary is to come next. For example, let's imagine if each word had a score showing how likely it is to be the next word in the sentence. This is where puzzle gets really interesting. Logits are passed to the softmax layer, which makes sure that all the scores add up to 1, like percentages. It is like turning those scores into a probability game, which asks which word is most probable to come next. The softmax layer outputs probability score for each word or token. This tells us the likelihood of each word being the next word in the sentence. Among all those probabilities, one word will have the highest probability. Sometimes this is calculated by greedy decoding technique, or there are some other algorithms used for it. This word is judged as the best guess for the next word in the sentence based on everything the decoder has learned from the input. Now let us look at the final flow. First, we tokenize the input words using the same tokenizer that was used to train the network. These tokens are then added into the input on the encoder side of the net, passed through the embedding layer, and then fed into multi-headed attention layers. Positional encoding is also added. The outputs of multi-headed attention layers are fed to a feed-forward network to the output of encoder. At this point, the data that leaves the encoder is a deep representation of the structure of input sequence. This representation is inserted in the middle of the decoder to influence the decoder's self-attention mechanism. The contextual representation from the encoder is used to initialize the decoder's hidden state or initial context. This step ensures that the decoder has access to the encoder information when generating the output sequence. A special token known as start of sequence token is added to the input of decoder. This token serves as initial trigger for the decoder to begin generating output sequence, and decoder component is similar to encoder. It also has a cross attention mechanism. The output of decoder's self-attention layers get passed through a decoder feed forward network and through a final softmax output layer. At this point, we have our first token. We continue this loop, passing the output token back to the input to trigger the generation of next token until the model predicts an end of sequence token and output is produced. I hope the content about LLM architecture was interesting. If you did like the video, do subscribe to our channel. Thank you.